All right, so I'm continuing along my solution in our Chapter 10 homework, which is exercise 10.1 through 10.5. So we just recorded a video related to 10.1 and 10.2. Now we want to look at 10.3. And so what's going on in 10.3 is when I look at my main Lotka-Volterra model, okay, we pointed out that this first term within my rate expression for my rabbits is my kind of exponential growth term, right? The rate of change of rabbits in the absence of foxes is proportional to the current population of rabbits. And so when we just solve this, right, we should expect an exponential function, an exponential increase in the population of rabbits as a function of time. And so what we want to do here in 10, we're going to look at this term individually. So we're going to solve, or 10.3, we're going to solve just the growth term in the absence of foxes. See that's an exponential function and think about if that's realistic. And then 10.4, we're going to update it with what's called a logistic growth equation. And we'll kind of talk about this as we go. So let me have at it, all right? And then once we kind of have played with this, then we'll come back to our Lotka-Volterra model in 10.5 and modify it accordingly. Okay, so if I'm going to solve a differential equation, I'm going to start by coming over here and I'm going to create a rate function. Okay, so function res, and I'm going to call this maybe rabbit growth. Okay, and it's a rate function, so we're going to have two inputs. First is my independent variable t, followed by my dependent variable. In this case, we're just playing with rabbits, so I'll just make it r, rabbits. Okay, cool. So I don't need to do any unpacking. Let me do my parameters. Okay, so my one parameter I have is a, which is 0.1. Okay. Now computing my rate. So I could use res. I could also make this drdt. It's all the same, and so it's just going to be a times r. Okay, cool. So there's rabbit growth. Okay, and now I'm going to solve this, and so I'm going to create a top function. So I'll create a function with no inputs, and so let me call this rabbit growth 10.3. I don't have any outputs, so I'm going to call it rabbit growth 10.3. Okay. Now let me start with my time interval. And we're going to do the same thing. So I'm going to go from a time of, so t naught would be 0. And it's t final 365. Yeah, also 365. So t final. I'm going to store them to variables just so my ODE 45 call makes sense. My initial condition, so R naught is equal to 100 still. Okay, and so we're going to solve. And so I'm going to store the output to variables from the onset. Oh, come on. Okay, that's going to be ODE 45. First argument is my rate function. So this could be rabbit growth, followed by my time range. So I'm going to integrate from t naught to t final. And then my initial condition, which in this case is just r naught. Oh, I want to suppress that output. And so then I'm going to plot. So I'll figure 1. And I'm going to plot R versus T as a black line. X label will again be time in days. And my Y label is going to be, I'll just call it population of rabbits. Okay, So if I solve, right, I get my plot. So here's my population of rabbits. Okay, and if I put my cursor over here, what I find at 365 days, all right, this is my exponential growth of a population of 7.10953 times 10 to the 17 rabbits. Okay, which matches that reference value. So in the absence of foxes, so if I'm solve my Lotka-Volterra model and I say there's no foxes, so in the absence of foxes, the population of my rabbits is going to grow exponentially. So the idea or the question is this is an ecosystem, right, in which I just have rabbits and foxes present. So I imagine I have some island, some island somewhere in the world where just rabbits and foxes are present. If I don't have any foxes, this is predicting that the rabbit population is going to grow exponentially, and over the course of 1 year, I'm going to have this, insane amount of rabbits. Okay, remember before we were peaking out at about 100 with both rabbits and foxes present. So the question is this physically reasonable? The answer should be, well, no, right? If I have an island, there's going to be a constraint on the available resources to support that rabbit population. If I had, 1 times 10 to the 17 rabbits, right, they're just going to consume every resource in the island and then they will all die off, right? That's not physically reasonable. And so that's what we're going to do in the next problem, right? So now when I look at 10.4, it's okay. This Lotka-Volterra model, it assumes an exponential growth of rabbits in the absence of foxes. It's not really physically reasonable. So one way we can try and improve it is we can introduce what's called the logistic growth model. And so what I'm going to do is I'm going to save this and I'm going to call this 10.4. Okay. And what's going to happen in my in 10.4 is I'm just going to update my rate so that instead of being this exponential growth term, we're going to replace it with this logistic growth model. Okay. So here is what I want my rate to be. So we're going to introduce additional constant k, and so we're going to start with the k of 150, and then we'll look at other values, right? So we're going to start with a k of 150. K corresponds to the carrying capacity. Okay, and we'll see what this means. But k is 150 is called the carrying capacity, and we'll see what it means. I'm going to specify it to be 150. And then my rate, I'm going to add in a term which is minus a divided by k times r squared. Okay, don't need the period there, but I'm going to add it. Okay, so what happens is I'm going to add this parameter k. I'm calling it my carrying capacity. I set it at 150. Let's look at what the effect of this is. Okay, so now if I just run it, okay, I get similar growth in my rabbit population, but then once I hit 150, the value plateaus off. Okay, so the idea behind the carrying capacity is that my ecosystem, right, can only support so many rabbits in the absence of foxes. All right, that kind of limiting value that my environment can support is dictated by what's called the carrying capacity. So my population of rabbits will increase unchecked, right? But it's going to have a limit of the growth, right? It can only grow, right, until it hits that carrying capacity, right? It can't exceed the carrying capacity of my system. Okay, so that was value 150, right? And the comment was the initial population was 100, so I have a carrying capacity greater than the initial population. So the question was, well, what happens if I change it to 50 and value lower than my initial population? As well, then, exactly as you'd expect, all right, you're going to have some death of rabbits, and you're going to plateau off at that carrying capacity because that's the maximum value that that ecosystem can support. Okay. So key is, right, is all I've done is I've modified my rate expression, right? So I have this first term, which is our exponential growth term, right? The rate of change of rabbits is proportional to the current population of rabbits. But then the second term, right, essentially introduces this behavior such that the maximum population I can actually observe or have, right, is dictated by this parameter k, which you call the carrying capacity. And so hopefully, right, that's a more realistic model, right, of having some finite number of rabbits, right? And it could be anything, right? You would fit this to, say, your model and some data you have, right? Maybe it's 1,000, right? And so you still have this, growth term, but then eventually the population plateaus off at 1,000, right? So the carrying capacity, right, is the maximum population that kind of ecosystem or environment could sustain in the absence of foxes, right? So rather than the population of rabbits growing uncontrollably, right, it has constraints. Okay, so the next video we will implement this within our Lotka-Volterra model, going back to our solution from 10.1, and we'll look at what the effect is. Okay, we'll see you in that last video.